Okay, okay. Okay, can you see my
Yeah.
screen now?
Yep.
Okay, okay, yeah. Okay, thank you, Francois. So
Okay.
can
So
I
just
start?
just to be sure, we agree on the rules. You've got 15 minutes
Okay, no
sharp.
problem.
Sharp.
Okay,
So if you shall not take more time than that, and then
okay,
we'll take 10 minutes to ask questions. Okay.
okay, no problem. Thank you, thank you.
Okay.
So we go. Uh, I'm Pengfei He, a student from the He University Danji, and supervised by Professor Jinkao Hao. I will take a presentation about my work, hybrid genetic algorithm for routine problems. Um, the first one is that we need to know what is the definition of the split delivery vehicle routine problem, or SDVIP. I think everyone knows the definition of the capacity vehicle routing problem, a very famous combinatorial optimization problem, where each customer should be served by only one vehicle exactly once. However, this constraint should be relaxed in the SDVIP because each customer can be served by more than one vehicle. So look at this example of SDVIP. This street customer is served by two vehicles, the blue one and the green one. This problem includes two versions: the SDVIP with limited fleet and unlimited fleet. Given that this problem is a computational challenge, so there are several existing heuristic algorithms for large-sized instance, such as iterated local search, taboo search, and hybrid genetic algorithm. Furthermore, this problem was also addressed in Denmark's implementation challenge last year, and our algorithm won the second place at this challenge. Here is the framework of our algorithm, a split MA. Given a start population, crossover is applied to produce several offspring solutions, and each one is improved by local search and managed by the population management. The most important part of this algorithm is the general edge assembly crossover. So let's introduce it. First of all, we need to use the multi-graph to define each SDVIP solution. Since each customer can be served by more than one vehicle, so there may be parallel edges between two vertices in the SDVIP solution. Look at the figure 1, solution 5A. There are three edges between vertex I and vertex J. For each SDVIP solution, we must use the multi-graph to denote it. Then we also need to define the degree difference. Given two solutions, phi A and phi B, let GA and GB be the corresponding multigraphs. Look at figure 2A. Here are two solutions, phi A and phi B. The vertex I in solution phi A is associated with a degree of 6. It links 6 edges in solution. However, in the solution phi B, the vertex I is associated with degree of 4. Thus, the degree difference of vertex I in solution phi A and phi B can be defined as delta I, which equals the absolute value of degree AI minus degree BI. So in the figure 2, in this figure, we can easily find data I equals 2 and data j also equals 2. If we want to make the data I equals 0, the most easy way is to add a dummy loop II in corresponding solution. For example, there is a dummy loop II in solution 5b. Why we need to define the degree difference? We need to give some explains. The first one is that using promising edges is a good choice to produce offspring solutions. And the second one is that we want to use the famous crossover, the edge assembly crossover EAX, to produce offspring solutions. Indeed, this crossover was initially designed by Nagota when solving the TSP and VIP. We also know each city or customer in these solutions should be solved exactly once in all feasible solutions. So each vertex is associated of degree of 2. And then EX can use this property to assemble edges to produce high quality offspring solutions. But for the SDVRP, this property cannot be satisfied. So we have to define the degree difference and make the degree difference of each vertex become 0. Thus, the EX can be applied. After adding dummy loops in corresponding solutions, such as dummy loop II and JJ, we can build a joint multi-graph GAB, which is the symmetric difference of EA and EB. So in the step 1, we want here is the step 1, the illustration of the GEX crossover. In this step, the common edges between the EA and EB are removed firstly, and the non-common edges are solved in the GAB. So in the step 2, all edges in a joint multi-graph GAB are divided into several AB cycles. The process is very simple. For example, for the AB cycle 1, firstly, random vertex is selected such as this vertex, and then edges from 5A and 5B are linked alternatively to form a cycle. This edge belongs to EA and EB, so we can have AB cycle. In the next step, these AB cycles are combined together to produce several E sets. In the step 4, we can produce several intermediate solutions. Given a number of E sets and a basic solution such as 5A, we can the same number of intermediate solutions. For example, for the solution A prime, it can be produced by the E set A and the basic solution 5A. Firstly, the common edges between these two items are removed, and then non-common edges are solved to form the solution A prime. In the next step, all isolated subtools in intermediate solution are eliminated. For example, here is a triangle subtool. Finally, we have several offspring solutions. Then, for each offspring solution, we have to repair customer demand and the capacity of each router. The mutation, local search, and population management are used to involve the population to find the better global best solutions. In our experiments, 9 reference algorithms and 4 sets of benchmark incidents are used to evaluate the performance of our algorithm for both the SDVIP with limited fleet and unlimited fleet. Here is the experiment. Here are experimental results. Our algorithm can update 143 new upbounders out of 324 instances. Furthermore, we also carried out experiments to analyze the rationale behind the GX crossover. Indeed, this crossover can totally solve all common edges from high-quality parent solutions to offspring solutions. While it can also introduce some diversity by assembling non-common edges. Look at the Figure 6. We can easily find high-quality solutions share more common edges. So this property can provide evidence that our crossover can inherit more useful information from parent solution to offspring solutions. Additionally, we also carried out experiments to investigate the benefits of the maximum split per customer. Imagine that in the SDVIP, if a customer is served by too many vehicles, it means that in this solution, this customer will link too many edges, which may be harmful to the quality of solutions. So in our algorithm, we try to limit the maximum splitters per customer. After adding this constraint, the performance of our algorithm is improved significantly. Furthermore, the mimetic algorithm were also applied to the min-max MTSP, and experimental results also in our experimental results, our algorithm can update 83 new upbounders. Additionally, this framework was also applied to the TSP's various profits for solving both the orienteering problem and price collecting TSP. For the orienteering problem, our method can update 67 new low bounders, and for the price for the PCTSP, 120 new upbounders are updated. Here is the conclusions of my work. The most important is that the crossover is a general operator for routing problems. Besides, it can be applied to the TSP very profit. It can be also applied to the location routing, arc routing, and directed routing problems. Furthermore, in my algorithm, the maximum number of splitters per customer are limited. So when solving routing problems with a split delivery, this constraint can be added to improve the performance of meta-heuristics. Thank you for your listening, and here is my presentation. Thank you all.
Okay, thank you for your presentation. So it's time for questions.